So let's continue our discussion of Chapter 4, Mass to Mole Conversions. In this chapter, we're now moving on to multi-step conversions. In this case, we're combining our previously learned steps of mass to mole conversions, mole to mole conversions, and mole to atom conversions. To show another example of this multi-step conversion process, let's take a look at the following problem. We're asked how many atoms of oxygen are in a sample of glucose. We're given the formula that has 43.55 grams of hydrogen. Okay, so we're given the grams of hydrogen, and at the end of this whole process, we want to report the atoms of oxygen. Now, how in general do we calculate atoms? How do we calculate atoms?
Moles.
Moles, yep. So we're going to go to the moles of oxygen. Now, given that we have the formula, where can we get the moles of oxygen from if we start with the grams of hydrogen and we know our chemical? Sorry, I'm noticing a little bit of reverb. Oh, never mind, it's gone away now. So just to repeat that, how can we calculate the moles of oxygen if we know our chemical formula and we're given the initial mass of hydrogen?
Ratio.
Yep, so then that mole to mole ratio, using the formula, we can get the moles of oxygen from the moles of hydrogen. The formula allows you to convert between the moles of one element in the formula and the moles of another element in that same formula. So now that we have this set up, we're going to execute on this unit conversion. So we have 43.55 grams of hydrogen. To go from grams of hydrogen to moles of hydrogen, we know in 1 mole of hydrogen, we have 1.00 grams. Now, looking at our chemical formula, if we want to go from the moles of hydrogen to the moles of oxygen, how many moles of oxygen per mole of hydrogen do we have in this case? What is our mole to mole ratio given the formula of glucose? What are the number of oxygen and hydrogen atoms in glucose?
6 to 12.
Yep, exactly right. We have 6 moles of oxygen per 12 moles of hydrogen. Next, we need to go from the moles of oxygen to the atoms of oxygen. And how many atoms of oxygen are in a mole of oxygen? What number do we use?
Avogadro.
Yep, exactly right, which is 6.02 times 10 to the 23rd. So now we're going to punch this into our calculator. And please make sure to try entering these values into your calculator to make sure you're able to get the same output. So we take 43.55 divided by 1.00 times 6 divided by 12 times 6.02 EE23. And that gives us 1.3108 times 10 to the 25th oxygen atoms that we round to 4 sig figs, which gives us 1.311 times 10 to the 25th oxygen atoms. Does this make sense to everyone? Any questions on this example? Okay, so let's apply now what we've learned. And we're pretty familiar with mass to mole conversions. Let's talk about some more direct ways of performing mass to mole conversions. So let's talk a little bit about mass percent and mole percent. So if we think about a molecule, they're made of atoms of their component elements. And the percentage of each element in a compound can be written either as mass percent, which is the mass of the element over the total mass times 100%, or mole percent, which are the moles of an element over the total moles times 100%. So these are ways to represent the amount of each element in a compound, or the amount of an element in a sample. Okay, now what can we do with this information? What can we do with this information? Well, first, from the formula, we can calculate mole percent. So suppose we're given the formula of calcium chloride. Our first goal is to determine the number of each atom of each element from the molecular formula. So for example, in calcium chloride, I would have 1 calcium atom and 2 chlorine atoms. Okay, so from our chemical formula, we can determine the moles of each atom of each element and the total moles. So we can say that we have 1 mole of calcium, 2 moles of chlorine, and for our total, we have 1 plus 2, or 3 moles total. Okay, perfect. So now that we have the moles of each element, we can calculate the mole percent. So the mole percent of calcium in this case would be the moles of calcium over the total moles times 100%. So we have 1 mole of calcium over 3 moles times 100%, and that gives us 33.3%. The mole percent of chlorine, on the other hand, would be the moles of chlorine over the total moles times 100%, which is equal to 2 moles of chlorine over 3 moles total times 100%, which gives us 66.7%. As you notice, if we add up and if we look at the total number of moles of all atoms of each element, the mole percentages will add up to 100%. So that's just a way of checking your work. Does this example make sense to everyone?
Yes.
Perfect. So we can apply this same logic to calculate mass percent. So in calculating mass percent, we determine the moles of each element, and from the moles of each element, so for example, we have 1 mole of calcium and 2 moles of chlorine, we can then calculate the mass of each element using our atomic mass. So if we have 1 mole of calcium, we know that there is 40.00 grams per 1 mole of calcium, and that gives us 40.00 grams. If we have 2 moles of chlorine, we know that we have 35.45 grams per 1 mole of chlorine. And punching that into our calculator, that gives us 70.9 grams of chlorine. Okay, we can now calculate the total mass. So the total mass would be the mass of calcium plus the mass of chlorine. And that in turn gives us 110.9 grams total for calcium chloride. And now that we have the total mass, we can calculate the mass percent. So in this case, the mass percent of calcium, we get 40.00 grams of calcium over 110.9 grams of calcium chloride times 100%. And that in turn gives us 36.07%. The mass percentage of chlorine is equal to 63.93%. And as we see, if we add up our two mass percentages, they would add up to 100%. Does this idea make sense to everyone? Does this idea make sense? Is everyone comfortable with calculating mass percent and mole percent? Any questions that I can address? Okay, well, let's do an example where we're asked to calculate the mole percent of each element in nitric acid. Okay, so I'm going to draw a picture of nitric acid. Not entirely descriptive of its Lewis structure, just so I can count atoms. So I see from the formula, I have 1 mole of hydrogen, 1 mole of nitrogen, and 3 moles of oxygen. So then for my total moles, I have 3 plus 1 plus 1, or 5 moles. From this information, I can now calculate the mole percentage of each element. So the mole percentage of hydrogen, we have 1 mole of hydrogen over 5 moles total times 100%, and that gives me 20% for the mole percentage of hydrogen. The mole percentage of nitrogen, we have 1 mole of nitrogen over 5 moles times 100%. That in turn gives 20%. For the mole percentage of oxygen, we have 3 moles of oxygen over 5 moles times 100%, which in turn gives us 60%. Is everyone comfortable with calculating mole percent given the chemical formula? Any questions on this example? Is everyone feeling comfortable with this content so far?
Yes.
So let's also calculate the mass percent of each element in nitric acid. So we have HNO3. So for hydrogen, we have 1 mole of hydrogen. For nitrogen, we have 1 mole of nitrogen. And for oxygen, we have 3 mole of oxygen. To calculate the grams of hydrogen, we have 1 mole of hydrogen, and we know that we have 1 gram per every 1 mole of hydrogen. So that gives us 1 gram of hydrogen to work with. For our grams of nitrogen, we have 1 mole of nitrogen, and we know that we have 14.00 grams of nitrogen per every 1 mole of nitrogen. That in turn gives us 14.00 grams of nitrogen to work with. For the grams of oxygen, we have 3 moles of oxygen, and because oxygen has a mass of 16 gram per mole oxygen, again, this is obtained from the periodic table. This is the atomic mass, otherwise known as the molar atomic mass. That gives us 48.00 grams of oxygen. If we calculate our total mass, we'd have 48.00 plus 14.00 plus 1.00. And that in turn gives us 63.00 grams per mole of nitric acid. We can then calculate the mass percentage. So for hydrogen, we take our 1.00 grams of hydrogen over 63.00 grams of nitric acid times 100%.
Professor, it says mass percentage of hydrogen?
Yes.
Okay.
Mhm. Which is the mass of hydrogen over the total mass of our sample. So we take 1 gram of hydrogen over 63 grams total times 100%. And that gives us a percentage of 1.59%. For the mass percentage of nitrogen, we have 14.00 grams of nitrogen over 63.00 grams times 100%. And that in turn gives us 22.22%. Finally, for the mass percentage of oxygen, we have 48.00 grams over 63.00 grams times 100%. And that in turn gives us 76.19%. And you see that if you add up each of our mass percentages, using your calculator, that gives us a total mass percentage. Of 100%. So that gives us an indication that we've done these mass percentage calculations accurately. Does that make sense to everyone? Any questions on calculating mass percent? This is an example that can potentially show up on an exam or quiz.
Professor, when asked that question on a quiz, is it going to have the same terminology or like formation of how you ask it?
Yes, yes. Or it could be phrased like, what is the mass percent of nitrogen in nitric acid? In which case you'd only report the mass percentage of nitrogen.
Okay, thank you.
So let's apply what we've learned. So let's take about 2 to 3 minutes, and I'd like you to calculate the mole percentage of each element in dioxygen difluoride. So using the chemical formula, I'd like you to first calculate the mole percentage of each element in dioxygen difluoride. And we'll give ourselves 2 to 3 minutes, and I'd like to see some responses in the chat. And if you have any questions, don't be shy to ask your questions verbally. And it's great that we're seeing some responses in the chat. Let's keep working on this problem, and then we'll discuss in about another 2 to 3 minutes. And don't be shy to ask a question in the chat, or to share your responses verbally or in the chat. And it's great to see students sharing their responses in the chat. And we'll discuss this example in another minute.
Professor, may I ask a question about the naming this element?
Yes, yes.
Why is fluoride giving 2 to oxygen? Isn't fluoride has like minus?
But remember, this is a covalent compound as it has 2 or more nonmetals. And as a result, in the name, the atoms are not charged in the covalent compound. Rather, they're sharing their electrons to form covalent bonds. So in dioxygen difluoride, essentially we have a structure that looks like this. So there are no charged ions in this structure. Rather, it's a covalent compound where the atoms are sharing their electrons using covalent bonds.
Okay, got it. All right, thank you.
Why the formula is not just the FO, like simplest ratio?
Because the simplest ratio of atom rule, it's used when given the name and you're simplifying the formula for ionic compounds. Yes, you simplify the formula to the smallest ratio of atoms. But since covalent compounds, the formula is not derived from the charge. The formula is derived explicitly from the number of atoms of each element. You do not simplify the formula for a covalent compound.
Okay.
Mm-hmm. So let's talk about this example. So in dioxygen difluoride, so we see that our moles of oxygen, we have 2 moles of oxygen. And for our moles of fluorine, we have 2 moles of fluorine. To calculate our total moles, we have 2 moles of oxygen plus 2 moles of fluorine. And that in turn gives us 4 moles total. So in turn, the mole percentage of oxygen would be 2 moles of oxygen over 4 moles times 100%. That in turn gives us 50%. And then the mole percentage of fluorine, again, would be 2 moles of fluorine over 4 moles total times 100%, which would also give us 50%. And as we see, if we add up all of our mole percentages, we get 100%. Does this make sense to everyone? Any questions on this paper? Okay, so let's take what we've learned now and let's try to apply what we've seen, and let's try to calculate the mass percentage of each element in dioxygen difluoride. Same compound, except this time you're calculating the mass percentage. So let's work on this example for the next 2 to 3 minutes, and then we'll come together as a group to discuss. Don't be shy to ask any questions in the chat or to propose your responses in the chat or verbally, and I'd be happy to get your questions answered. And if there are any questions I can address, don't be shy to let me know. And let's try to get a few responses shared in the chat. And let's try to get some proposed mass percentages of each element in the chat, and then we'll discuss momentarily. And if you have a question, if there's any part that you're unsure about, don't be shy to ask a question verbally or in the chat, and I'd be happy to get your question answered. And it's great to see that we're starting to see some proposed mass percentages in the chat. Let's keep working on this example, and we'll discuss in another minute to a minute and a half. And if you have any questions working through this example, don't be shy to ask.
Professor, may I ask another question about naming? Sorry.
Please go ahead.
Why don't we call it difluorine oxide? Even the oxygen is on the right side, why we don't say it? Like difluorine oxide, dioxide, I mean.
This is a bit of a weird example. Typically, the more electronegative element is named second, is placed second in the name. But this is a bit of an odd case in terms of naming. In general, the more electronegative element is named as the second name in a covalent compound formula.
More electronegative.
Mm-hmm.
So if we go with that rule, so you name it correctly then, because fluorine is more, right?
Exactly.
Electronegative. Okay, got it. Thank you.
Perfect. So let's look at this example now. So given our formula, we see we have 2 moles of fluorine, and we know that fluorine's molar mass is about 19.00 gram per mole of fluorine. That in turn gives us 38.00 grams of fluorine. We have 2 moles of oxygen. So we have 16.00 grams per 1 mole of oxygen. That gives us 32.00 grams of oxygen. For our total mass, we have 32.00 grams of oxygen plus 38.00 grams of fluorine, and that gives us 70.00 grams total of our compound F2O2. We've essentially just calculated the molar mass. Okay, so now that we have that set up, we can calculate the mass percentage of fluorine, which will be 38.00 grams of fluorine over 70.00 grams of F2O2 times 100%. So we have 38 over 70. And that in turn gives us 54.29%. The mass percentage of oxygen, we take the mass of oxygen, which is 32 grams, over the mass of F2O2 times 100%. And that in turn, 32 over 70 times 100%. That in turn gives us a mass percentage of 45.71%. Again, when we add both of our mass percentages together, that gives us a total mass percentage of 100%. Does this example make sense to everyone? Does this example make sense to everyone?
Professor, why did you report with 4 sig fig? Because I thought the other numbers are just fixed numbers, like 30, like 16, and
so, well, an important thing to consider is that these molar masses, these atomic masses, are functionally exact numbers. They have more sig figs than even the amount of sig figs that we're writing out in this example. I used 4 sig figs because those are the number of significant figures that you'd see in the molar masses that I'll provide you in the exam periodic table. So I try to keep the formatting consistent. The main thing that I'm looking for in your answer is just that your mass percentage agrees with the number of significant figures for your mass values. Though I want you to keep in mind, these atomic masses are functionally exact. They have 10 or more significant figures. They've been determined to a high level of precision. We're just cutting it off at 4 sig figs, just so that way the atomic masses don't trail on and we don't have to write out these really, really long numbers. When the point of the problem is to calculate the mass percent, you take the mass of your sample over the total mass, which is obtained by adding up the mass of both elements in your sample. Yes, that's exactly right. Does that make sense?
so my question is, if we have the only number in the problem is the atomic mass, we always round to 4 sig fig, right?
Yes. Well, you look at the number of sig figs that you're given in your periodic table, and you round to the same number of sig figs.
Okay, got it. Thank you.
And the table that you're going to receive on the exam, all the atomic masses are going to be reported to 4 sig figs. Does that make sense?
It does. Thank you.
Perfect. So to show how we'd calculate this 54.29, you'd first enter 38.00 in your calculator, then you'd hit the division symbol and enter 70.00. Then you'd hit the multiplication symbol, and then you'd type in 100 times 100, and then you'd hit the equal sign. When you enter it that way into your calculator, do you reach the same result that I have? Perfect. And if you need any other help entering any of these calculations into your calculator, just let me know and I'd be happy to show you. Okay, so let's keep going now and let's talk a little bit about how we can leverage mass percent as a conversion factor. So mass percent is defined as the grams of element in 100 grams of sample, or the grams of compound per 100 grams of sample. So what mass percent allows us to do, it allows us to go from the mass of a sample to the mass of an element, or the mass of a sample to the mass of a compound. So let's showcase this rearrangement. So if the mass percent is equal to the grams of element over 100 grams times 100%, then we know that the grams of our element is equal to the mass percent and rewriting. So rewriting this, outside of us assuming that we have a 100-gram sample, we can also write the mass percent as the mass of our element over the mass of our sample. And we can calculate the mass of our element by taking the mass percent over 100% times the grams of our sample. So this is another way of calculating the mass of an element given the mass percent and the mass of our sample. I'm going to show you the conversion factor method because I find it's more scalable and it's more applicable to a range of problems. So if we have a 35.5 grams of sample that is 23.5% silicon, we're asked what mass of silicon is present in the sample. So we're trying to go from the grams of our sample to the grams of silicon. And the conversion factor that we're going to use is the mass percentage. So if we have 35.5 grams of sample, this mass percentage of 23.5% is essentially saying that we have 23.5 grams of silicon per every 100 grams of sample. This is a textbook form and conversion factor form of the mass percent. Does everyone notice how when we're calculating the mass of silicon, that these two equations, the equation obtained from the conversion factor method and the equation obtained from the algebraic method, these two equations are the same. They look exactly the same in terms of formatting. So as we can see from our units, the grams of sample cancels and we're left with the grams of silicon. So we punch this into our calculator. We have 35.5 times 23.5 over 100. And that in turn gives us 8.34 grams of silicon. So you can write any mass percentage as the grams of that component over 100 grams of sample. And by writing mass percentage as a conversion factor, we can use the same logic of unit analysis to solve these problems. Does that make sense to everyone? Does this idea make sense? Any questions on this? Okay, so just like any other conversion factor, we can fit in mass percentage into multi-step conversions. So in this case, we are given the grams of our sample and we are given the mass percentage of carbon and we're asked to calculate the moles of carbon. And to do that, we simply calculate the grams of carbon. Now that we have our solution map established, now all we have to do is execute on that. So if we have a 20-gram sample, to go from the grams of sample to the grams of carbon, we use our mass percentage, which tells us we have 13 grams of carbon per every 100 grams of sample. Once we have converted to the grams of carbon, to go from the grams of carbon to the moles of carbon, that's just our molar mass. And we know in 1 mole of carbon, we have 12.00 grams. So punching this into our calculator, so we have 20 times 13 over 100 divided by 12. That gives us 0.216 moles of carbon that we round to 0.2 moles of carbon. Does this example make sense? Does this example make sense?
Professor, what is this 13% carbon? Could you explain that part? This is 13 gram over 100 grams?
Yep, exactly. So if we think about 13% by mass, so another way of writing this calculation is that the grams of carbon would be equal to the mass percentage of carbon over 100% times the grams total. So what this 13 over 100 is representing is this component of our conversion factor. So another way to visualize this, so if it's 13% by mass and you have a 100 gram sample, if you have 13% of 100 grams, that percentage slice would be 13 grams, right?
Yes, okay.
So then we can rewrite this mass percentage as the mass in 100 grams of sample. Does that make sense?
Yes, it does. Thank you.
Perfect. Any other questions I can address? Yes, 0.216 is correct, but then we round because our input has 1 sig fig. So your calculations are correct. It just is rounded because our input only has 1 sig fig. Does that make sense? Perfect. So let's keep going with this, and we can utilize a pretty interesting principle in solving these problems. The mass percent of each component element should total to 100%. So for example, if a 15 gram sample is analyzed and found to contain 14% carbon, with the remaining mass being fluorine, how many moles of fluorine are present in the sample? So in this case, we are starting out with our grams of sample, and we're asked to calculate the moles of fluorine. So to do that, we're going to go through the grams of fluorine. Now, we know that the mass percentage of carbon plus the mass percentage of fluorine must add to 100%. Ergo, the mass percentage of fluorine is equal to 100 minus the percentage of carbon, which is 14%. That gives us a mass percentage of fluorine of 86%. So now that we have this set up, we have all the tools that we need to complete this unit conversion. So starting off, when we have 15 grams of sample, we know that for 15 grams of sample, let's look at our solution map. We're asked to go to the grams of fluorine. Given our percentage by mass of fluorine is 86%, we know we have 86 grams of fluorine per 100 grams total. That's our mass percentage conversion factor that we calculated. Next, we can go from the grams of fluorine to the moles of fluorine. And we know in 1 mole of fluorine, we have 19.00 grams. So punching this into our calculator, we have 15 times 86 over 100 over 19. And that in turn gives us 67.89% that we then round to not percent. Whoops. I multiplied by 100. Got a little ahead of myself there. So punching this into our calculator, that in turn gives us 0.6789 moles of fluorine that we then round to 0.68 moles of fluorine. Does that make sense to everyone?
Yes.
So just to repeat, we calculated the mass percentage of fluorine because we're told in the problem it contains only carbon and fluorine. So then the remaining mass percentage must be the total mass percentage minus the mass percentage of carbon. That gave us the mass percentage of fluorine of 86%. Using the mass percentage of fluorine, we can go from the grams of sample to the grams of fluorine. And then from our molar mass, we can go from the grams of fluorine to the moles of fluorine. We round to 2 sig figs because our input has 2 sig figs. Does that make sense to everyone?
Yes.
Okay, so then let's try to apply what we've learned, and I'd like you to tackle the following example, where a 30-gram sample was analyzed and found to be 30% sulfur, with the remaining mass being oxygen. And I'd like you to tell me how many moles of oxygen are present in the sample. And everyone's able to hear me okay from the Zoom stream, right? There are no issues with lag or anything like that?
You cut off a couple times for a couple seconds.
Okay. Is it consistent now?
It's good now.
Okay. If there are any issues with that, just let me know. And I'll make sure to try to modify the settings so the stream is as consistent as possible. So let's work through this example, and we'll take about 3 to 4 minutes to work through this example, and then we'll come together as a group to discuss. Don't be shy to ask questions and to propose your answers verbally or in the chat. And it's great to see students sharing their responses in the chat. And we'll discuss this example in about another 2 to 3 minutes. And if you have a question when you're working through this example, don't be shy to ask it verbally or in the chat. And if you have any questions, don't be shy to ask. And we'll discuss this example in another 1.5 to 2 minutes. And I just want to make sure everyone has enough time to draw their conclusions and to have their problem-solving proposal written down. So that way when we go over this problem, we can have a reasonable discussion. I see a large number of the class has responded in the chat. Thank you for doing so. We're now going to discuss this example. So in this case, we're given the mass of our sample. So we're given the grams of our sample. And we're asked to calculate the moles of oxygen. We can get the moles of oxygen from the grams of oxygen. So in order to get the grams of oxygen, we're going to need the mass percentage. So to calculate the mass percentage of oxygen, we're going to take 100% minus the mass percentage of sulfur. So we have 100% minus 30%, which gives us 70% for the mass percentage of oxygen. So now that we have this set up, we can execute on this conversion. So given that we have 30 grams of sample, we know from our mass percentage to go to our grams of oxygen, we have 70 grams of oxygen per 100 grams of sample. Then to go from our grams of oxygen to our moles of oxygen, we use our molar mass. So we know in 1 mole of oxygen, we have 16.00 grams. Now that we have plugged in all our conversion factors, all we have to do is execute. So we take 30 times 70 over 100 divided by 16. That in turn gives us 1.3125 moles of oxygen that we round to 1 mole of oxygen, as we only have one significant figure in our input. Does that make sense to everyone? So to enter this into your calculator, you'd take 30, then you'd hit the multiplication symbol, followed by 70, then you'd hit the division symbol, followed by 100, then you'd hit the division symbol again and enter 16. Does that make sense? Perfect, perfect. So let's look at an advanced example where we perform some multi-step conversions using mass percent. So we're going to read through this problem and we're going to tackle it step by step. So in the first case, we're given the following information. A 2-gram tablet of aspirin is 16.3% acetylsalicylic acid by mass. And we're asked to calculate the mass of acetylsalicylic acid in the tablet. So I'd like you to try to start off this problem using our idea of mass percentage as a conversion factor. The only thing that's new in this example is rather than being given the mass percentage of an element, you're given the mass percentage of a compound. So let's work on this example for about 1.5 minutes and 2 minutes. Let's just try to get this first part of the example complete and submitted. And I'd be happy to answer any questions, and I'd love to see some responses in the chat for the first part of this question.
What does MW mean?
The MW this is just the molar mass. MW is an abbreviation for molecular weight or molar mass. So let's work through this example and let's try to get a few reasonable responses for the mass of acetylsalicylic acid in the sample, given that we have a 2-gram tablet that is 16.3% acetylsalicylic acid by mass. And we'll discuss this example in about 1.5 to 2 minutes. So let's try to get a few responses in the chat for the mass of acetylsalicylic acid given the mass percentage. And we'll discuss this example momentarily. And for now, we just want the mass of acetylsalicylic acid in the tablet. And let's try to get a few responses in the chat before we discuss. Okay, so let's discuss this example. So in this case, we're given the mass of our tablet and we're asked to calculate the grams of acetylsalicylic acid, which has the following formula. So to go from the total mass to the mass of an element or compound, we're going to use the mass percentage. We're going to use our mass percentage. So given that we have a 2-gram tablet, we know for the mass percentage, we have 16.3 grams of acetylsalicylic acid per every 100 grams of sample. Punching this conversion factor into our calculator, plugging our conversion factor into our calculator, we have 2 times 16.3 over 100, and that gives us 0.326 grams of acetylsalicylic acid. As we're doing a multi-step conversion, we're going to retain all of our digits, but if we had to round, we'd round this for reporting our final answer as 0.3 grams. Does this make sense to everyone so far? Does everyone?
So 100 gram of what?
So this is the grams of our tablet. So this would be 100 grams of the tablet.
Oh, okay.
Mass percent as a conversion factor is defined as the mass of our component over the total mass of our sample. In this case, the sample is the tablet. Does that make sense?
So does the aspirin contain salicylic acid?
Yep, exactly. Yep, that's the major active component of aspirin. So now that we've calculated the mass of acetylsalicylic acid, I'd like you to take this mass value and I'd like you to calculate the moles of acetylsalicylic acid in the tablet. I'd like you to calculate the moles of acetylsalicylic acid given the mass. And let's take another 2 to 3 minutes and let's try to convert our calculated mass value into the moles. So given the mass of acetylsalicylic acid, I'd like you to work towards calculating the moles. Don't be shy to submit your responses in the chat or any questions that you have in the chat, and we'll discuss in about 1.5 to 2 minutes. And it's great to see that we're observing reported moles calculations in the chat. We'll give everyone about another minute to work on this problem where we're calculating the moles of acetylsalicylic acid given the mass, and we'll discuss this example in about another 30 seconds to a minute. Okay, so let's discuss this example. So in this case, we're asked to convert from the grams of acetylsalicylic acid to the moles of acetylsalicylic acid. So given that we have 0.326 grams of compound, and we're given that the molar mass is 180 gram per mole, we know that in 1 mole of acetylsalicylic acid, we have 180 grams. So plugging this in, we have 0.326 over 180, and that gives us 0.001811 moles of acetylsalicylic acid. If we had to report our final answer after rounding, we'd round this to 0.002 moles, just because our original input number only had 1 sig fig. Does this make sense to everyone so far? Does everyone see how this problem is testing each of our unit conversions that we've seen so far in this class? Does this make sense to everyone so far? Can I get some confirmation in the chat that everyone's comfortable with how we've approached and solved this problem so far?
Yes.
Perfect.
With the significant figures.
Yes, because our original mass of the tablet had 1 sig fig,
Uh-huh.
all of our
Oh, with the 2 grams. Scott. Okay, that makes sense now.
perfect.
Thank you.
So let's keep going with this example. We're just carrying through our value through multiple unit conversions. In this case, now we're asked to calculate the moles of oxygen in a 2-gram tablet, given that we have 0.01811 moles of acetylsalicylic acid. So I'd like you to convert the moles of this compound into the moles of oxygen. And again, let's take another 2 to 3 minutes to work on this example. And this is the same type of mole to mole conversion using the chemical formula that you've seen time and time again. And don't be shy to share any questions or responses that you have in the chat. I'm looking to see that we have a reasonable pool of class responses for this next mole to mole conversion before we continue. And just as a refresher, we're going from the moles of our compound to the moles of oxygen using our chemical formula. And it's great to see that the class is contributing their responses in the chat. And we'll discuss this example in another 30 seconds to a minute. Okay, so let's discuss this example. So to go from the moles of a compound to the moles of an element, we use our formula ratio. So we have 0.001811 moles of acetylsalicylic acid. And my question to all of you is, in our formula, how many moles of oxygen do we have in 1 mole of our compound? 4, yep. Exactly right. Everyone see the 4 oxygens? So punching this into our calculator, we have 0.001811 times 4. and that gives us 0.007244 moles of oxygen. And we could round this based on our sig fig rules to one significant figure because our original input had one significant figure. Does this example make sense? Does this make sense to everyone so far? Any questions so far on this example?
Professor, I'm just a little confused on, given that, so basically, how did you get the 0.001811?
This is the same problem from before. We're just continuing this problem.
Oh, I see.
Does that make sense?
Yes, okay. I was thrown off, sorry.
We're just continuing the problem from before, carrying through what we calculated in the earlier parts of this problem. Does that make sense? Perfect. Any other questions on this example? Okay, so let's take, given the moles of oxygen, let's work on calculating the mass of oxygen in a 2-gram tablet. So let's take about another 2 to 3 minutes and let's calculate the mass of oxygen in a 2-gram tablet, given that we've already calculated the moles. Don't be shy to share your responses in the chat, or if you have any questions that I can address, don't be shy to ask your questions verbally or in the chat. And it's great to see a reasonable pool of responses. Let's give everyone another 30 seconds to a minute to complete this mole to mass conversion, and then we'll discuss. Okay, so in this case, we're asked to go from the moles of oxygen to the grams of oxygen. If we have 0.007244 moles of oxygen, we know that we have 16.00 grams per mole of oxygen. And that in turn gives us 0.1159 moles of oxygen that we round to, oh, sorry, not moles, grams, because moles cancel. And we round that to 0.1 grams of oxygen. Does this question make sense? Does this part of the question make sense? Okay, so let's keep going. And now as a final capstone for this question, I'd like you to calculate the mass percent of oxygen in the tablet given that the mass of the tablet is 2 grams. So let's spend about 2 to 3 minutes on this final part of the question, and then we'll discuss together as a class.
So we calculate the total mass.
The total mass is given in the problem to be 2 grams.
Oh, okay.
Mhm. So let's keep working through this example, and if you have any other questions or if you have a proposed response for this problem, don't be shy to message in the chat. And it's great to see that we have a pool of responses in the chat. So let's now discuss this example. So mass percent is defined. So the mass percentage of oxygen in this case is defined as the grams of oxygen over the grams total times 100%. So we know we have 0.1159 grams of oxygen. And we know that we have a total mass in our tablet of 2 grams. Sorry, just resizing this. So multiplying by 100%, that gives us, so we take 0.1159 over 2 times 100, and that gives us a percentage of 5.795% that we round to 6% by mass. So a typical aspirin tablet, assuming acetylsalicylic acid is the only source of oxygen, has roughly 6% oxygen by mass from the acetylsalicylic acid. Does this example make sense? Does this make sense to everyone? Any questions on this example? Okay, so let's do another somewhat higher level example. So ethanol has a density of 0.789 gram per mil and was found to have the following percentages of each element by mass. And our first goal of business is to determine the mass of hydrogen in 0.1 liters of ethanol. Let's take about 3 to 4 minutes to work on this problem. And if you have any questions setting up this problem, don't be shy to ask in the chat. Remember, the density allows us to convert between the mass and volume of a sample. So let's work through this example and we'll discuss in about 3 to 4 minutes. And don't be shy to share your proposed responses in the chat or to ask any questions in the chat or verbally. I want to make sure everyone has practice on the most difficult types of questions that I could ask from this chapter, just so that way we have a fair preparation coming into the exam. As you see, if you break the problems into pieces, they become much more manageable. We've seen all of these little pieces before. So let's keep working on the first part of this question, and we'll discuss momentarily. So to help with the setup, write out what values you are given, what your starting value is, and then focus on what final value you're aiming to calculate. So once you have your starting and ending value, then you can figure out what intermediate units or what conversion factors do I have in the problem that let me go from my starting quantity to my ending quantity. It's great to see that students are starting to share their responses in the chat. We'll keep working on this example and we'll discuss in about another 1.5 to 2 minutes. And don't be shy to share any questions you have or your proposed responses in the chat. Okay, so we're given the volume of ethanol. So we have 0.1 liters of ethanol. And in the end, we're asked to calculate the grams of hydrogen. We can calculate the grams of hydrogen, given our mass percent, from the grams of ethanol. And we can calculate the grams of ethanol using the density from the milliliters of ethanol, because the density allows us to convert between the volume and the mass. So now that we have our conversion map set up, we have 0.1 liters. We know in 1 milliliter, we have 10 to the negative third liter. And then to go from our volume to our mass, we utilize our density, which is 0.789 grams of ethanol per 1 milliliter. Then to go from grams of ethanol to grams of hydrogen, we use our mass percent. So we have 13.1 grams of hydrogen for every 100 grams of ethanol. So punching this into our calculator, we have 0.1 divided by 1 EE negative 3 times 0.789 times 13.1 divided by 100. And that in turn gives us 10.3 grams of hydrogen that we in turn round to 10 grams of hydrogen to respect the fact we only have one significant figure. Does this example make sense to everyone? Does this example make sense to everyone? Any questions on this example?
The one significant figure comes from the 0.1 liter.
Yes, exactly right. Any other questions on this example? Perfect. And now as a follow-up, this should be pretty quick actually. I'd like you to tell me the moles of hydrogen in our sample, given that we have 10.3 grams of hydrogen. Let's calculate the moles of hydrogen in our sample. And as we can see, this is a pretty fast conversion because in 1 mole of hydrogen, we have 1 gram of hydrogen, and that gives us 10.3 moles of hydrogen, which we round to 10 moles of hydrogen. Oh, one moment, OneNote had a small stutter. Give me 1 second to reload OneNote. Perfect. Can everyone still see OneNote at this point? Can everyone see my screen?
Yes.
Okay, perfect. Sorry about that. Sometimes when there's a lot of things drawn on OneNote, it can sometimes get slightly overwhelmed. Okay, so we have 10.3 grams of hydrogen, and we know in 1 mole of hydrogen, we have 1 gram. That in turn gives us 10.3 moles of hydrogen that we round to 10 moles of hydrogen. Does this example make sense to everyone? Does this example make sense? Any questions on this example? So as we can see, you've tackled some relatively difficult examples and essentially have applied all of the concepts that we've covered in this chapter to perform multi-step mass to mole conversions. This is about as hard as it's going to get for an exam. So if you study the examples that we've covered throughout this chapter, you should be more than okay. Any other questions? Any other questions on this problem? If not, let's keep going to our next major topic, which is the empirical and the molecular formula. So, looking at the empirical and molecular formula, most analytical methods provide us the mass or mole ratio of elements in a sample or the mole and mass percent of elements in a sample. The mass percent, mole percent, mass ratio, or mole ratio are used to calculate the empirical formula. So the empirical formula is the simplest formula that contains the smallest whole number ratio of elements that make up a compound. So the empirical formula can be thought of as the smallest whole number mole ratio of each element. So for example, in P2O10, we have 10 moles of oxygen for every 2 moles of phosphorus, and that could be simplified to 5 moles of oxygen to 1 mole of phosphorus. So our empirical formula would be PO5. For C3H6, would someone like to propose an empirical formula for C3H6?
Say H2.
Yep, exactly right. The empirical formula would be CH2. How did we get that? So 6 moles of hydrogen per 3 moles of carbon. This 6:3 ratio simplifies to 2 moles of hydrogen per 1 mole of carbon. Does that make sense? Does everyone see how to figure out the empirical formula from the molecular formula? Does that make sense to everyone?
Why we needed to make it to empirical formula?
Well, sometimes it's important to, well, most of the time, experimentally, the empirical formula is what is calculated from experimental data. And it's important to be able to identify the empirical formula for different compounds, because in many cases, a set of 2 different compounds can have the same empirical formula. And as a result, you can recognize and sort of determine what additional experiments need to be performed in order to fully assign the identity of your compound. Does that make sense? It's also setting the stage for a calculation that we're going to do from mass data. So if you think of the empirical formula as a mole to mole ratio, that idea will serve you well later on in this chapter. Does that make sense?
Yes.
Perfect. So now a separate experiment is done to determine the molecular weight and to calculate what is known as the molecular formula, where the molecular formula, rather than being the simplest ratio of atoms, is the absolute number of atoms of each element in a compound. Molecules can have the same empirical formula with a different molecular formula. So this is part of why being able to recognize empirical formulas is really important, because the empirical formula is not necessarily unique for a given compound. So in N2O4, the empirical formula would be NO2, because we have 4 moles of oxygen per 2 moles of nitrogen. That simplifies to 2 moles of oxygen per 1 mole of nitrogen. In NO2, our empirical formula is NO2. So as we can see, these 2 different compounds have the same empirical formula. Does that make sense to everyone? Does that make sense to everyone so far? Perfect. So the empirical formula is repeated n times to give what is known as the molecular formula, where n is the number of empirical formula units, mW is the molar mass or molecular weight, and what we can do is from the molar mass, from the mass of our compound, and from the empirical formula mass, we can calculate the number of formula units. So, to give you an example of how this works, if the empirical formula of hydrazine is NH2 and its molecular mass is 32, let's figure out how many formula units that we have. So NH2, we can calculate the empirical mass. So let's calculate the empirical mass of NH2. So we take the mass of nitrogen, which is 14 grams per mole of nitrogen, and we have one nitrogen atom. We have 1 gram per mole hydrogen, and we have 2 hydrogen atoms, and that in turn gives us an empirical mass of 16 grams per mole of NH2. So we plug in our empirical mass, then we plug in our molecular mass, and as we see, we get a value of N of 2. I'll pan up in a moment. Let's just finish this thought for now. So what this N equals 2 is saying is that we have 2 NH2 units. So then what we do is we take each of our atom counts, each of our subscripts, and we multiply it by 2 to give us N2H4. And this would be our molecular formula. Does that idea make sense? By calculating N, it tells us how many of these empirical units that we have, and so we multiply our empirical formula by N to get our molecular formula. Another way to visualize this is if we think about NH2NH2, we can simplify it to N2H4. Does that make sense? Does this idea make sense of how we calculate the molecular formula from the empirical formula and the molar mass? Can I get some confirmation in the chat for this? Okay, so just to show the earlier part of the notes, as a student requested this, could you let me know in the chat once you've finished writing down the portion that you need? Also, all of the notes are recorded, and once we finish a chapter, the annotated notes will be reported and posted onto Canvas. Any questions while students are writing down and continuing to write down parts of their notes?
So empirical mass is the same as molecular mass.
The empirical mass, it's a very specific molecular mass. It is the mass of the empirical formula unit, while the molecular mass is the mass of our entire molecule with all of the empirical formula units in it. Does that make sense?
Yes.
Perfect. So, to make sure everyone's comfortable calculating the molecular formula, I'd like you to look at the following example. So the empirical formula of benzene is CH, and its molecular mass is 78 gram per mole. I'd like you to tell me, and I'd like you to calculate the molecular formula of benzene. So let's take about 3 to 4 minutes to work on this example, and then we'll discuss. And don't be shy to share your questions or your proposed responses in the chat. Let's try to get a few more proposed formulas in the chat, and then we'll discuss shortly. Perfect. We see a pool of responses from multiple students suggesting the formula for benzene is C6H6. So let's talk a little bit about the logic behind this. So our empirical formula unit is CH. So then the empirical mass would be equal to 12 grams times 1 plus 1 gram times 1, which gives us 13 grams per mole of CH. From this now, we can calculate N by taking our molecular mass of 78.0 gram per mole divided by 13 gram per mole. That gives us an N of 6. So we take our CH units and we multiply them by 6. That in turn gives us C6H6 for our molecular formula. Does that make sense to everyone? Does that make sense to everyone? Is everyone comfortable with this example? Any questions? Perfect, perfect. So this is a good stopping point for today. And what we're going to do is we're going to take a small break and then we'll meet again for a lab where we'll have a lot of time in this lab to work on some of the problems that I've assigned. I've posted a series of workbook pages for students to work on, and I've also opened up the optional nomenclature quizzes. And so the plan would be in lab that we can work on some of those assignments and that I can answer any of the questions that you have. We're closing out chapter 4 and we're going to start chapter 5 on chemical reactions next week. I have the notes ready to post. I just wanted to make sure they were released at a time when everyone finished up chapter 4 so we don't end up mixing and covering the content out of order. So the extra credit quizzes are available on Canvas and they'll be due not this Sunday but next Sunday, just so that way you get the practice down before we have our next exam. The next exam will be tackling that once we finish up the next 2 chapters. And you'll see an announcement a week in advance on Canvas.